Welcome back to Asterisk Data on Demand Asterisk, the show where we ask the big questions about privacy, security, and how technology might let you keep your asterisk data in your own pocket. Literally. I'm Sam, and joining me are Alex and Taylor. Today's topic is a future-proof vision, storing everything locally and letting third parties see only what you explicitly allow. And with an optional government-sanctioned middleman that can prove the data was stored safely asterisk and verify authenticity before handing off any piece of it, we'll dig into how such a system could actually work, what tech would be required, and what blind spots we've probably overlooked.
Got it, let's dive in.
First off, let's broaden the horizon beyond medical records. Think of every category that people already have digital versions for: identity documents, health data, finance, legal papers, even the logs from your smart home or wearable. I'd add educational credentials, transcripts, course certificates, skill badges, and then there's digital assets like NFTs and crypto wallets. Even location history, travel itineraries, app preferences, UI themes, accessibility settings, all those little things that make up your digital persona.
And don't forget the big ones: driver's license, passport, national ID, employee badges, university diplomas, professional licenses, tax returns, bank statements, loan agreements, property deeds, insurance policies, wills, power of attorney documents, vaccination history, genetic data, mental health notes.
Exactly. The idea is to keep them in a personal vault, encrypted on your device or a home server you control, and decide who sees what and when. Picture the architecture with 3 concentric circles. At the core is the personal vault where everything is stored encrypted. Next comes the selective disclosure engine that can slice data, verify claims, and generate proofs. Finally, an optional government-sanctioned verification service sits outside to audit proofs without ever touching raw personal data.
The vault uses AES 256 GCM for the database, keys derived from a strong passphrase or stored in a TPM. It also keeps an immutable audit log of every read-write signed by itself. If someone tampers with the file, the hash chain breaks and you see it instantly.
For selective disclosure, we rely on verifiable credentials, a W3C standard where a claim is signed by an issuer and can be verified against a registry of trusted issuers. Then, zero-knowledge proofs allow us to prove possession of a credential or property. I am over 18, without revealing the underlying data. The third-party service, say an insurer, sends a proof request over HTTPS TLS describing required attributes. The vault checks that it has the requested VC, verifies the issuer's signature using its public key, then generates either a signed fragment or a succinct ZKP. That proof is sent back to the insurer.
If you want extra assurance, the proof goes through the middleman. The middleman first verifies the hash against an immutable audit log on a tamper-evident ledger, public blockchain or consortium chain, and checks that the proof was generated by a device with a valid attestation report from a trusted execution environment like Intel SGX or ARM TrustZone. Once verified, it returns a simple verified status to the insurer.
That's how authenticity can be guaranteed. If someone tampers with your local database, the Merkle root stored on the ledger will no longer match, and the system flags it. Fake credentials are rejected because each VC carries a digital signature from its issuer. If the issuer isn't in the registry, the proof fails. Counterfeits also get caught because the vault only ever accepts VCs that verify against the trusted issuer list. If a fake VC slips in, the verification step will fail, and you'll know it's bogus.
But we need revocation too. Credentials can become invalid, vaccination status changes, a license gets revoked. The middleman must expose a revocation registry or a refresh mechanism that the vault consults before accepting proofs.
Cross-border compliance is another nuance. Different jurisdictions have different data protection rules. The middleman should provide region-specific policies and maybe a jurisdiction-aware API so services know what's allowed in their country. Usability matters big time. Users don't want to manage raw keys. A password plus biometric unlock or a hardware wallet that abstracts key management keeps the UX simple while still protecting data.
Performance is also a factor. ZKPs can be computationally heavy on mobile CPUs. Using a TPM or secure enclave for proof generation helps, and pre-computed proofs for common claims can reduce load.
Privacy versus auditing. While the middleman never sees raw data, logging that a proof was requested could still leak patterns. Applying differential privacy to audit logs mitigates this risk.
Liability is another hidden cost. If a forged credential leads to fraud, who bears responsibility? Clear contracts between issuers, vault owners, the middleman, and third parties are essential.
And finally, think about offline scenarios. The system should allow pre-generated proofs that can be verified once connectivity returns, so low-bandwidth users aren't stuck.
To prototype this, you could start with a local vault like Nextcloud with encrypted files, or a self-hosted Aries agent for VC handling. Hospitals can issue signed VCs via OpenID Connect extensions. Build a simple REST API for the middleman that accepts proofs, verifies them against an issuer registry, and returns status codes. Wrap it in TLS and require client authentication.
If you want remote attestation, run your vault inside SGX or ARM TrustZone. Many cloud providers also offer trusted execution environments that can host your vault while still protecting data. Append each verification to a public readable blockchain as a Merkle root for tamper-proof logs.
Bottom line, you can store all sensitive data locally, keep it encrypted, and let third parties see only what you explicitly allow. By combining verifiable credentials, zero-knowledge proofs, trusted execution environments, and a neutral verification service that never touches raw personal data, we get a privacy-preserving yet auditable ecosystem.
The key challenges now are usability, robust revocation mechanisms, cross-border compliance, and building governance so the middleman remains truly neutral. If those hurdles can be cleared, the vision of personal data sovereignty becomes realistic.
That's all for today. Thanks for listening. Stay curious, stay secure, and keep your data in *your * hands.